Welcome to the Explainer. We're going to talk about the hidden forces inside something as simple as a soda can. But to get there, we actually need to start with something way more dramatic, like a burst pipe.
Okay, so let's kick things off with a bit of a mystery. Look at this pipe. It didn't just break. It kind of unzipped itself right along its length. Now, why would it do that? Why not just snap clean in half? The answer, it turns out, is this incredible engineering principle that, believe it or not, keeps our whole world from flying apart. So, to get to the bottom of this mystery, we've got to talk about the physics behind all sorts of containers we use every single day. We are officially diving into the world of pressure vessels.
So what is a pressure vessel? Well, it's pretty much any container that's designed to hold gases or liquids at a pressure that's way different from the pressure outside. You know, think about big industrial boilers, or the propane tank for your grill, or even just a simple can of hairspray. They're all engineered to handle some seriously immense forces from the inside.
Okay, so how do they actually do that? How do they hold all that pressure in? Well, you can think of the wall of the container as being in this constant, invisible battle. It's always pushing back against the force that's trying to blow it wide open. And that internal pushback, that resistance that's holding everything together, that's what engineers call stress. But here's where things get really interesting. When you're talking about a cylinder, like our pipe or a soda can, that stress isn't just one single force. Nope. It's actually two totally separate forces, and they're pulling in completely different directions.
All right, first up, we've got something called hoop stress. I want you to picture a bunch of invisible hula hoops wrapped around the cylinder. The pressure inside is pushing out on every single one of those hoops, trying to stretch them until they snap. And if they snap, the cylinder splits open lengthwise, just like that pipe we saw.
And then there's the other force. It's called longitudinal stress. This one acts along the length of the cylinder, from end to end. Its whole goal is to push the caps off. It's literally trying to pop the top and bottom right off the can.
Okay, so let's just recap real quick. We've got hoop stress, which is trying to unzip the can down the side, and we've got longitudinal stress, which is trying to uncap it at the ends. Two totally different forces, right? And that means there are two totally different ways for one of these things to fail.
But, and this is the big reveal, these two stresses are not equal, not even close. In any cylinder, one of them is always, and I mean always, stronger than the other. And the secret to which one? Well, it's all in the math.
So the formula for hoop stress is pretty straightforward. It's just the pressure, P, times the radius, R, all divided by the thickness of the wall, T. Simple enough, right?
Okay, now look at the formula for longitudinal stress. It looks almost exactly the same, but you see it? Look at the bottom. The denominator, it's not just T, it's 2 times T.
Do you see what that means? That one little 2 on the bottom of the fraction, it changes everything. It tells you exactly which one of these forces is the bigger deal.
It means the hoop stress is always exactly twice as big as the longitudinal stress. Let that sink in. The force that's trying to unzip the can is literally double the force that's trying to pop the ends off. 2 to 1.
And look, this isn't just some textbook theory. It's a fundamental rule of engineering for these kinds of pressure vessels. You could almost call it a law of physics for how these things are going to break.
And that brings us full circle, right back to our unzipped pipe. Things break along the path of greatest resistance, or in this case, greatest stress. Since the hoop stress was double, boom, the pipe unzipped. Mystery solved.
So that totally explains why cylinders fail the way they do. But, it also brings up a really important question for an engineer, right? If a cylinder has this built-in weak point, is there a better shape, a stronger one?
Well, what about a sphere? A sphere is it's a perfect shape. Because it's completely symmetrical, the pressure inside pushes out evenly in every single direction. That means the stress in the wall is the same everywhere you look. There's no hoop versus longitudinal, it's just one uniform stress.
And the math just spells it all out for us. Remember, the maximum stress in a cylinder was that hoop stress, PR divided by T. Well, for a sphere, the stress is PR divided by 2T. So for the same pressure, same material, same everything, a sphere is just naturally twice as strong as a cylinder. How cool is that?
This makes a sphere the absolute king, the most efficient shape there is for holding pressure. And that's exactly why when you see tanks for storing stuff under super high pressure, like natural gas, they're often these giant spheres. Yeah, they're more difficult and expensive to build, but you get double the strength for your trouble.
So, this whole 2-to-1 rule, it's not just some abstract thing you solve in a physics class. It's an invisible principle that is absolutely critical to the design of so many things we see and use every day.
Hey, have you ever actually looked at a propane tank? The ends aren't flat, are they? They've got these rounded, dome-shaped ends. That's not just to look nice, it's a super clever bit of engineering. You get the easy-to-manufacture cylinder for the main body, but you cap it with the strength of a sphere to handle the stress. It's the best of both worlds.
And once you see it, you'll start noticing this design logic everywhere. It's in aerosol cans, in scuba tanks, industrial boilers, even the main body of an airplane. And yep, it's in the humble soda can too.
And really, understanding these two basic stresses, that's just scratching the surface. Engineers take these fundamental ideas and use them to figure out much more complicated stuff. I mean, think about something like this ski gondola hanger. It's getting pulled, bent, and twisted all at the same time. You have to start with the basics to figure that out.
So next time you pop open a can of soda, maybe you'll think about that invisible battle going on inside. Our world is just full of these hidden principles, these clever engineering tricks that are all designed to balance forces and, quietly keep us safe. And it really makes you wonder, doesn't it? What other amazing feats of engineering are just hiding in plain sight?